In section 15.4, we are going to discuss the reaction quotient. When we use capital K, that represents the ratio of concentrations or partial pressures of products to reactants in a system at equilibrium. And large Kc values, or K values greater than 1, the equilibrium is shifted to the right, so more products are going to be there if it's in equilibrium. For small K values, much smaller than 1, the equilibrium is shifted to the left, so at equilibrium more reactants are present. So what happens if the system is not at equilibrium? Well, we use the reaction quotient instead, and that can be determined using the same exact ratio as K, or equilibrium constant, but using concentrations or partial pressures when the system is not in equilibrium. So it's the same process, but K is at equilibrium, and the capital Q is when it's not at equilibrium. So here's the example we saw previously when we were setting up our equilibrium constants. So here's just a generic equation or reaction. The reaction quotient expressed for this reaction for concentration is the exact same way we would set up the equilibrium constant. So it would be the concentration of your products divided by the concentration of your reactants. And if you were dealing with pressures, it would be the exact same method. We could also predict the direction in which the reaction will shift by comparing the values of Q and K. When Q is equal to K, the reaction is at equilibrium and there will not be a shift. So what's happening is, for these types of equations, we're changing something. We're changing a concentration, we're changing a pressure. And when that happens, you've upset the reaction and it wants to do everything in its power to get back to equilibrium. So we're trying to estimate and see which way will it shift to reach that equilibrium. So if Q is greater than K, more reactants must be formed to achieve equilibrium and the reaction will shift left. And if Q is less than K, more products must be formed to achieve equilibrium and the reaction shifts right. So for these types of equations, you're going to be solving for Q and comparing it to K to estimate this. Here's a figure that shows the differences in Q's and K's. We have just a mock equation. We have two circles, and then they combine to have the double circle in the products. So let's look at figure A. Q is less than K. And if we see what's in solution, we have a lot more of our starting material than our products. So if we want this to reach equilibrium, we're going to have a lot more products made. So that's why we say that the reaction is going to shift towards the right, because we want to have those products made to get back to equilibrium. B, we have equal amounts of starting material as we do products. So that just shows that it's already at equilibrium and it will not shift any further to reach more stability. And then lastly, part C, we see that we have a lot more products in solution than we do reactants, and that's when Q is greater than K. So what it wants to do to get back to equilibrium is it's going to create more reactants, so then it has stability. So that's what it's important to note that if Q is less than K, then products are favored. If Q is greater than K, reactants are favored. Example 15.8, they give us the Kc at 22 degrees Celsius for this decomposition. It says calculate QC for this reaction when the reaction mixture contains these concentrations. So because it does not say at equilibrium, that tells us this has to be a Q. So sometimes they won't even say calculate Q. They'll just say these are the concentrations, but they won't say at equilibrium. For it to be at equilibrium, you would need the concentrations at 22 degrees Celsius, since that's when it's at equilibrium. Let's set up our Q expression. So our QC will just be concentration of Br2 times the concentration of Cl2 divided by the concentration of BrCl squared. So now we can just plug in those values. And make sure when you're plugging this into your calculator to make sure your parentheses are correct. So you could always just do the top first and then the bottom, but that's always where I find the most errors are happening when I get these results. You set up the equation right, but sometimes there's always that one little math error, so that would just help you a lot. So for QC, I get 5.26, and KC is 377. So Q is smaller than K. So we found that QC was smaller than KC, and part B says, is the reaction at equilibrium? Well, that's not possible. For it to be at equilibrium, your Q needs to equal K, and since that's not for this case, it is not at equilibrium. And then it says, if not, will it proceed to form more reactants or more products? Well, since Q is a lot smaller than K, it's going to want to form more products. It's going to want to shift towards the products or shift right in order to get back to equilibrium. So I'm going to circle, form more products.